Hello everyone. In the previous class we discussed about Euclidean domain and principal ideal domain. We'll continue that discussion. Today we're going to study about principal ideal domain and unique factorization domain. We have already defined principal ideal domain. An integral domain is said to be a principal ideal domain if every ideal of this domain is principal ideal. What is meant by unique factorization domain? An integral domain is said to be a unique factorization domain if every non-zero and a non-unit element satisfies two conditions. The first condition is that element can be written as non-zero non-unit element can be written as product of finite irreducibles. Say A equal to P1, P2, P3, etc. up to Pn. And the second condition is the decomposition in this one is unique up to associates. That is, suppose A is equal to Q1 into Q2 etc. up to Qm is any other factorization of A as product of irreducibles, then number of elements in these two factorization must be same, and for some renumbering of the factors, Pi and Qis are associates. Now we'll move on to next proposition. In a principal ideal domain, a non-zero element is prime if and only if it is irreducible. Consequently, we have to show that in a PID, every non-zero prime ideal is maximal. Okay, let's prove the first part. We have already proved a result which says that in any integral domain, every prime element is irreducible. So this way is true. If it is prime, then it is simply irreducible by the earlier results. So we have to prove the other way. What is that other way? Suppose if that non-zero element is irreducible in a principal ideal domain, then we have to show it is prime element. Okay, let X be an irreducible element of a principal ideal domain R. Then we have to show that X is a prime element. But we know that we have proved result which says that if you want to show any element as a prime element, it's enough to show that the ideal generated by that element is a prime ideal. So if we want to show that X is a prime element, it's enough to show that principal ideal X is a prime ideal. But in fact, we'll show that the principal ideal X is a maximal ideal of R. What is meant by maximal ideal of R? Suppose this principal ideal X is contained in some ideal I, which is contained in the ideal R, that is nothing but the ideal generated by 1. Let us assume this one. Then we knew that R is a PID. So every ideal of R must be a principal ideal. So I is also an ideal of R. Therefore, I must also be a principal ideal. Let's assume I is equal to the ideal generated by A for some A belongs to R. Now we are having a situation, the ideal generated by X is contained in ideal generated by A, which is contained in ideal generated by 1. But we knew that the smallest ideal which contains X is principal ideal X. Therefore, X belongs to principal ideal X, which is contained in principal ideal A. Therefore, X is also belongs to principal ideal A. But any element of principal ideal A must be of the form A into some number. So let's assume X equal to multiple of A, that is A into B for some B belongs to R. But we knew that we have chosen X as an irreducible element. By the definition of irreducibility of any element, one of these two must be unit. Either A is a unit or B is a unit. Now, suppose if A is a unit. If A is a unit, then principal ideal A will be equal to principal ideal 1. They should be equal. On the other hand, if B is a unit, then your x equal to A into B, where B is a unit, by the earlier propositions, this is of the form A equal to B into U, then A and B are associates. By that proposition, your x and A will become associates, but we knew that if x and A are associates, then the corresponding ideal generated by x and A must be equal. So, in any of the situation, the condition of maximality holds. Therefore, the ideal generated by x is a maximal ideal. And we knew that in an integral domain, every maximal ideal is a prime ideal. So, this is a prime ideal of R. This completes the proof of first part. See, let P be a non-zero prime ideal of a principal ideal domain R. Then, since P is a principal ideal, it has to be an ideal generated by some element. Let's say it is generated by P. Since this is prime ideal, every element of this must, this element P must be a prime element. But just now we proved that every prime element in PID is irreducible. Therefore, this is irreducible. So, the ideal generated by this irreducible element P is a maximal ideal. Therefore, this ideal is a maximal ideal. So, we have proved the ideal, that is in a PID every non-zero prime ideal is maximal. So, this completes the proof. Now, in Z of x, we knew that we have proved the ideal generated by x is prime but not maximal. So, in general, we can say every maximal ideal is prime ideal in an integral domain, but every prime ideal need not be maximal. So, since this is not maximal ideal, by the above theorem, Z of x is not a PID. And we have proved that the ideal generated by 2x is not a principal ideal in Z of x. If this is a PID, then every ideal must be a principal ideal. So, this condition is violated, therefore, this is not a PID. No, in a PID and hence in a Euclidean domain, there is no distinction between prime elements and irreducible elements. We can call prime element or irreducible element. Both are one and the same. Now let's go for a corollary. Let R be a principal ideal domain and X be a non-zero element of R, then the following are equivalent. Suppose X is irreducible, then X is prime element. Just now we proved that in a PID, irreducible element implies it is nothing but a prime element. Therefore, by the above theorem, this result is trivial. And X is a prime element implies principal ideal X is a prime ideal. By the earlier results which we have proved, if this is a prime element, then this ideal is a prime ideal. This is true. Then if this is a prime ideal, then principal ideal X is a maximal ideal. In the above result we have proved, if this is a prime ideal, this is a maximal ideal. So we are through, and we knew if this is a maximal ideal, then X is irreducible. This implies this. Why? By the earlier result which we have proved, X is an irreducible element if and only if principal ideal X is a maximal ideal among all proper ideals of R. By that result, this is true. So we have proved all these are equivalent. Now let's move on to a proposition. Suppose R is a principal ideal domain and A and B are any two non-zero elements, then if the GCD ideal generated by D is ideal generated by A plus ideal generated by B, then we have to show that D is the GCD of A and B, and further D can be written as linear combination of E and B, A and B for some lambda and mu in R. Now, given that the ideal generated by D is equal to ideal generated by A plus ideal generated by B, but this ideal contains the ideal generated by A. So, the ideal generated by A is contained in ideal generated by D. But we knew that the smallest ideal which contains A is the principal ideal A. Therefore, A belongs to this, but this is contained in D, principal ideal generated by D. Therefore, A belongs to principal ideal generated by D, but any element of this is a multiple of D. So A will be equal to D into some number, but by divisibility property, that implies that D divides A. Similarly, the ideal generated by B is contained in this, but the smallest ideal which contains B is principal ideal B. Therefore, B belongs to principal ideal D, but any element of this must be of the form D into some number. So B equal to D into some number, but by divisibility definition, that implies that D divides B. So the first condition of GCD is satisfied. D divides A and D divides B. That is, D is a common divisor. Now, if D dash is any other common divisor of A and B, then we have to show that D dash divides D. Now, D dash divides A means A will be equal to D dash into some number. But any element which is a multiple of D dash should come in this ideal. Therefore, A belongs to this ideal. But the smallest ideal which contains A is principal ideal A. And we are saying A belongs to this. Therefore, principal ideal A is subset of this. Similarly, this implies this. Now, A belongs to this and B belongs to this. Therefore, principal ideal A plus principal ideal B belongs to this. But that is nothing but your principal ideal D. Therefore, principal ideal D is subset of principal ideal D dash, which implies that D dash divides D. So, we have proved the second condition of GCD. Therefore, D is the GCD of A and B. And in the earlier result, we have proved that every Euclidean domain is a principal ideal domain. And there we have shown that D can be written as a linear combination of A and B in R. The same result follows here. Now I had given exercise. You just go through this exercise and write it in an assignment. Now the next proposition is, in a unique factorization domain, an element is prime if and only if it is irreducible. But we know that in an integral domain, every prime element is irreducible. Unique factorization domain is also an integral domain. Therefore, every prime element is irreducible in UFD also. Therefore, this way is true. If it is prime, then it is irreducible. No need to prove that one. So it is only enough to show that every irreducible element in a UFD is prime. Let's prove that. Let X be an irreducible element of a UFD, and since we have to show it is a prime element, the definition of prime element says if P is a prime element, then if P divides AB, then P has to divide A or P has to divide B. By that, let us assume that X divides AB. But by the divisibility definition, X divides AB implies AB equal to X into some C for some C belongs to R. Now, let us write A, B and C as product of irreducible whenever they are non-units. Because in the UFD definition, we can write any element of R which is non-zero and non-unit as a product of irreducible. Because of that reason, if these are non-units, then we can write as a product of irreducibles. Now by the definition of UFD, clearly the associates of X will appear as an irreducible factor of either A or B, because X has to divide AB. So suppose if you assume A is factorized into P1, P2, etc. up to N, and B is factorized into some Q1, Q2, etc. up to Qm. Then if X divides Pi for some I, because they are associates, then X divides A, and if X divides Qj, then X divides P. So we are getting X divides AB implies X divides A or X divides B. Therefore, X is a prime element. This completes the proof. Now, we are having a remark here. In a UFD, the prime elements and irreducibles are identical. They are one and the same. But we refer to them as primes in Z or Z of I. But in f of x, we call them as irreducible polynomials. Now, these are exercise I had given. You work it out and write it in the assignment. Next theorem is every principal ideal domain is a unique factorization domain. So they are given a principal ideal domain and we have to show that it is unique factorization domain. Let R be a principal ideal domain. Now, if you want to show unique factorization domain, we have to show that every non-zero, non-unit element of U of D can be factored into product of finitely many irreducibles, and the second condition is that decomposition is unique up to associates. Okay, we have to show those conditions, but before that we show one ascending chain condition. What is that ascending chain condition? There is no infinite sequence of ideals in R in which each term properly contains the previous one. That is, there is no infinite chain of ideals such that I1 is contained in I2, I2 is contained in I3, I3 is contained in I4, etc. In properly. Let's prove this one. Let us consider chain of ideals of R. Say I1 is contained in I2, I2 is contained in I3, I3 is contained in I4, etc. In. Now let us put I as union of all these ideals, k from 1 to infinity ik. Then we have to show that I is an ideal of R. So first let us prove I is an ideal of R. What are the ideal conditions? First, it has to be additive subgroup. And the second condition, if you take any element from ideal and an element from ring, the product should be again in the ideal. Okay, let's prove that condition. Now let x and y be any two elements of I. Since x and y are belonging to union, x and y must be present in at least one of the ideal. Let us say x is present in some ideal is and y is present in some ideal it. Now since s and t are indexes for any two integers, s and t are integers, for any two integers, there are three possibilities are there. Either s is equal to t, or s is less than t, or s is greater than t. Let's assume for the time being s is less than or equal to t. In the same fashion you can prove for the other one also. Suppose s is less than or equal to t, then according to this, your is, which comes first, must contained in it. Now we should note that our x is present in is, but our is is contained in it. Therefore x is also present in it, y is also present in it, and your it is an ideal. Therefore x minus y must be present in it by the definition of ideal it. But this ideal it, is, all of them are contained in the union, and that union is I. Therefore this it is also present in I. Therefore x minus y belongs to I. We have proved I is an additive subgroup of R. Now let's prove the second condition. Suppose x is an element in I and R is an element in R. You know that x is an element in I means x must be present in the union. So x must be present in at least one of the ideal. Let's say is for some s. Since is is an ideal, an element of ideal into an element of ring, Rx as well as XR again comes in is. But all the ideals I1, I2, etc., all of them are present in this union. Therefore is is also present in this union. That means is is subset of I. Therefore Rx, XR, which are present in is, are also present in I. Therefore we have shown the second condition of ideal. Therefore I is an ideal of R. Now we have shown the union of these ideals is again ideal. Since R is a principal ideal domain and I is an ideal of R, every ideal must be a principal ideal. Therefore I should also be a principal ideal. Let's say some D, principal ideal generated by D. Now the smallest ideal which contains D is principal ideal D. Therefore D belongs to I. But I is nothing but union ik. So D belongs to this union. That means D must be present in at least one of the ideal. Let's say it is present in some IM. So your D belongs to IM. But basically D is an element which is present in I. Now we are saying D is present in IM. Therefore, this ideal I is subset of Im. That is, I is equal to principal ideal D, which is subset of Im. But by this condition, Im is contained in Im plus 1, Im plus 1 is contained in Im plus 2, etc. All of these are present in this union. Therefore, all these ideals are subsets of I. Now, we have started with I and end up with I. Therefore, the last two ideals are equal, means all of them must be equal. Hence, we have Im is equal to Im plus 1 is equal to Im plus 2, etc. That means the ideal starting from Im onwards, this is one and the equal, same. That means this is not an infinite chain. It is finite chain. It is from I1 to Im. Because remaining are one and the same, therefore we can stop at this stage. Therefore, this is a finite chain. That means this ring R has no strictly increasing chain of ideals. That is, no infinite chain. Suppose A belongs to R such that A is non-zero and non-unit. After proving this ascending chain condition, now we are proving the conditions of U of D. So, by the definition of U of D, we have to consider a non-zero and non-unit element. So, we are taking A is a non-zero and non-unit element. Then we have to show that A can be factored into finitely many irreducibles. So, we have to show that, we first show that A has an irreducible factor. Suppose A itself is irreducible, then there is nothing to prove. We are through. So, suppose if A is not an irreducible element, then we knew by the definition of irreducibility, if A is irreducible, then A equal to BC, where either B or C is a unit. But since A is not irreducible, A can be written as sum A1 into B1, where both of them are non-units. Both of them are non-units. Then A, we knew that this is multiple of A1. Therefore, this is present in the ideal generated by A1. Therefore, A is belonging to principal ideal A1. But the smallest ideal which contains A is principal ideal A. Therefore, principal ideal A is contained in principal ideal A1. But since B1 is a non-unit, if B1 is a unit, then your A is irreducible. Since this is non-unit, your principal ideal A is clearly proper ideal of principal ideal A1. Now, if A1 is not irreducible, if it is irreducible, we are through. If it is not irreducible, then we can write A1 as product of non-units, A1 equal to A2 into B2, and we've obtained this by the similar fashion. If A2 is not irreducible, then we can extend this chain. But remember, in the PID, ascending chain condition holds. That means this chain must stop after finitely many steps. Let's say it stops at an ideal generated by AR. That is, the ideal generated by A is properly contained in ideal generated by A1, properly contained in ideal generated by A2, etc. up to ideal generated by AR. See, the ideal generated by AR is contained in ideal generated by AR. AR minus 1 is contained in ideal generated by AR. But that implies that this AR divides AR minus 1. Similarly, AR minus 1 contains AR minus 2. So that implies that AR minus 1 divides AR minus 2. Similarly, this A ideal generated by A is contained in ideal generated by A1. But the smallest ideal which contains A is principal ideal A. Therefore, A belongs to this, therefore A belongs to this. But this is of the form A1 in any element of this one is of the form A1 into some number by divisibility property. A1 divides A. So A1 divides A. AR divides AR minus 1, AR minus 1 divides AR minus 2, etc. A1 divides A. By divisibility conditions, AR divides A. By transitive conditions of divisibility. Thus, AR is an irreducible factor of A. Now, we show that A is a product of finitely many irreducibles. If A is irreducible, then there is nothing to prove. If A is not irreducible, then by the above, A has an irreducible factor, say P1. That is A equal to P1 into C1, where P1 is irreducible. Now, what about C1? C1, if C1 is unit, then A becomes irreducible, this condition. But we are saying A is not irreducible, therefore C1 cannot be unit. So C1 is not a unit. Then again by the same earlier result, C1 is irreducible, then we are through. If C1 is not irreducible, then C1 can be written as P2 into C2, where P2 is irreducible. We are writing this one by this result. P2 is irreducible and C2 is non-unit. If C2 is unit, then we are through. Otherwise, if C2 is non-unit and not irreducible, then we'll continue this process. Thus, we can construct a chain of ideals such that by this, the ideal generated by A is contained in ideal, properly contained in ideal generated by C1, which is properly contained in C2, etc. But since the ascending chain condition holds, this chain must terminate after finitely many steps. So let's say it stops at ideal CR, ideal generated by CR. Hence we have A equal to P1, P2, etc. PR into CR. Now you just substitute C1, you'll get P1 into P2 into C2. By that way, we can write this one as P1, P2, etc. up to PR into CR, which is a factorization of A as product of finitely many irreducibles. So we have factored a non-unit non-zero element of R as product of finitely many irreducibles. This is the first condition of unique factorization domain. Now let's prove that this factorization or this decomposition is unique up to associates. Let us assume that A is factored into two types, P1, P2, etc. up to Pn, Q1, Q2, etc. up to Qt, where P1, P2, etc. up to Pn, Q1, Q2, etc. up to Qt are irreducibles. But we know that in the PID, every irreducible element is prime. That is what the result which we have proved earlier. So all Pi's and Qj's are prime elements of R. And since these two are integers, n and t, these indexes are integers, one of them must be less than this or both may be equal. Let us assume for the time being that n is less than or equal to t. Now we knew that P1 is a prime element which divides product of these. But P1 into P2 etc. up to Pn is equal to Q1, Q2 etc. up to Qt. Therefore P1 must divide Q1, Q2 etc. up to Qt. But since the, P1 is a prime number, prime element, by prime property, P1 must divide one of them. Let us say P1 divides some Qj for some j. By the similar fashion, your Qj must divide Q1, Q2, etc. up to Qt, but that is equal to P1, P2, etc. up to Pn. So Qj must divide one of them. So that number is some P1. Therefore, P1 and Qj are associates. After renumbering, we may take Qj as Q1 itself. Therefore, we can write Q1 as U1 into P1. This is of the form, if A and B are associates, then A can be written as B into some U, where U is a unit. In that form, they have written Q1 is equal to U1 into P1. Hence, we have, if you substitute this in this, P1, P2, etc. up to Pn is equal to U1, P1, Q2, Q, etc. up to Qt. P1, P1 cancels by cancellation law. Therefore, we left out this. Repeat this argument since n is less than or equal to t, number of p's, since n is less than or equal to t, number of p's must be less than or equal to number of q. Suppose if number of p's are less than number of q's, then after n steps, your p1 cancels, p2 cancels, etc. up to pn cancels. You left out with 1. So u1, u2, etc. up to un. And qn up to qn, it gets cancelled. So remaining is qn plus 1, etc. up to qt. Since none of the qj is unit, and you are saying product of these two is 1, this has to be unit. But this is not possible because qj is not a unit. Therefore, your n cannot be less than t. In fact, it should be equal to t. If it is equal to t, then your q1 is equal to u1 into p1, q2 is equal to u2 into p2, etc. Qn equal to un into pn. Therefore, pis and qj's are associates in some order. Thus, this factorization is unique up to the associate. So we have proved both the conditions of u of t, hence R is a u of t. That means in general, every principal ideal domain is a unique factorization domain. So if you if you see the results which we have proved earlier, and if you summarize it, then we can say every integral domain need not be u of d, but every u of d is an integral domain. Every u of d need not be a principal ideal domain, but every principal ideal domain is a u of d. Every principal ideal domain need not be a Euclidean domain, but every Euclidean domain is a principal ideal domain. Every Euclidean domain need not be a field, but every field is a Euclidean domain. For this, I'd given exercise. You just work it out, and you can see z of square root of minus 5 is not a u of t. Z of x is a u of t but not PID. This is PID but not a Euclidean domain. And these three are Euclidean domains, but these are not fields. Thank you.